Hey folks, Mrs. White here. I'm hoping that things went well with your Chapter 5 test. I saw a couple people during the review session, and I got a couple questions via email, so hopefully the test went smoothly and you turned it in. My goal is to grade those tests and have them up as soon as possible. I'm kind of waiting for the last couple of them to get handed in, and then I will release the corrected tests back to you folks, okay? And just so you know, that Chapter 5 test was kind of the last big test for the year. We are going to start Section 6.1 today, and Chapter 6 is the last chapter that we usually cover, which is great. We're actually in really good shape for the end of the year right now, but we're really only going to cover Section 6.1 today. And then we're going to cover 6.2 on Monday. And then what that means is that next Wednesday we are going to do 6.2 practice. Okay. And then we're going to review for our last quiz, and we're going to take a little quiz just to end up the year. So today and Monday are our last 2 days of brand new learning. Okay. So that's pretty darn exciting too. So Chapter 6 has us looking at exponential functions specifically for your class. So today we're going to start by talking about what does the graph of an exponential function look like? What is an exponential function? And then you can see here it's kind of sandwiched in between some of this Khan Academy practice. This Khan Academy practice is your homework, okay? So your goal is to pass both of these Khan Academy skills with a 75 or higher. And remember, because some of you aren't from my original math class, it's really important that you take screenshots when you pass it, and that's going to be what you submit on the Google Classroom, okay, folks? So exponential growth versus decay, and then we'll learn about the parent functions and how to actually go about graphing exponentials, and then you'll hop back on Khan Academy and do some exponential growth and decay graphing. Okay, so your goal is to really only do 4 of each of these, right? And then get at least a 75 or higher on each of them. If you end up not earning that 75, you do need to go back and practice it a little bit more. But I don't want this to monopolize your time. So if you spend more than 30 minutes working on either of these skills, then take a break. Pop me an email and show up to office hours and we can make something work, okay? But if you wait till really late on Sunday night to pop me an email saying you need help, obviously I'm not going to be available for you folks, okay? I'm old. I go to bed early. So I already kind of let you know that your test grades are up. They should be at least on PowerSchool, and I will hand back your corrected tests to you folks once I get the rest of them in. So exponential growth and decay is actually kind of a hot topic right now. If you have read or kind of looked into anything about coronavirus or COVID-19, they've talked a lot about how we need to flatten the curve. And the curve, if we're being specific, is this curve right here, exponential growth. And exponential growth happens when things double or triple or quadruple. So instead of like adding 2 every time, like a linear function, right? It goes up by 2, it goes up by 2, it goes up by 2. An exponential function is going to double or triple every time. So, for example, its graph would look something like this. It's going to increase really, really steeply. And as people talk about flattening the curve, we already had some information for this, and they're hoping that instead of having things double, maybe we can start having it look like this. Because eventually these exponential functions get really steep really quick. So kind of by eliminating certain people in the train of command, right? If this person isn't infected, then none of these people get infected as you kind of branch out from there. If this person doesn't get infected, then these 2 people don't get infected, and so on and so forth. And I don't want to talk this whole lesson about how it can be applied to coronavirus. In fact, I usually teach it with kind of thinking about the zombie apocalypse, a little Walking Dead reference. So that's what we're going to focus on looking at today. So it's kind of nerdy, but I actually really like this video by this guy, but he gets into some more information than you need. So we're going to watch a quick video for the next 8 minutes to kind of explain how exponential growth comes about and how we can model it with a graph and with an equation.
Matt, thank you again for stopping by. I am pumped that you are joining us on this lesson where we get to explore exponential growth in the context of the zombie apocalypse. Hey there, everyone. Thank you again for stopping by here at Mashup Math on this lesson where we get to explore exponential functions and just how fast a population can grow or how fast a population can decay. Now, as grim as this situation may be, Let's see how we can use our math skills to model it and figure out just how long it would take for the entire US to become the undead. Now, before we look at a population as big as the United States, let's start out with a group of just 100 people, and this is before any incident. So our human population would be 100, and our zombie population would be 0. So we can visually model this population of 100 humans using a grid with a length of 10 and a height of 10. So this 10 by 10 grid represents 100 normal human beings. Now at this point, everything is okay until some incident happens and one member of that human population becomes infected. We refer to this as patient 0, and now our human population drops to 99, and our zombie population is 1. And now here comes the chaos. That first infected person will inevitably infect a second person. So now our zombie population has grown to 2 infected individuals, while our human population has dropped to 98. And now we can see how, as this process continues, where the zombie population continues to double, we can see just how quickly the zombie population can grow while the human population simultaneously shrinks. So now we can see just how quickly an infection can spread, and now we are left with a zombie population of 100 and a human population of 0. They have completely taken over. Now, if we look at the growth of our zombie population on a graph, as time increased, the zombie population continued to double, and if we express this with a line, it would have to be a curved line and not a straight line, since this is an exponential relationship and not a linear one. Now on the same graph, let's also show the population of humans as time increases, which decreases by half each time until we are whittled down to 0. Notice that these graphs intersect, and that point of intersection represents the moment when the human population and the zombie population are equal. In other words, we have a 1-to-1 ratio. So for every human, we have a zombie. Now again, these graphs are curves, so they represent exponential functions. In the case of the zombie population, we can call this exponential growth, and in the case of the human population, we can call it exponential decay. So we have one population rapidly increasing over time and another rapidly decreasing over time. So if we want to model growth or decay using an equation, we have to use one in the form y equals a times b raised to the x power. Notice here that our variable is an exponent, which is what makes an exponential equation unique. Now, when we graph an exponential growth equation, our graph is going to be a curve that often resembles a hockey stick, where the initial growth is slow and almost linear, but quickly becomes extremely rapid and exponential. Note that in such equations, the a value always has to be greater than 0. Now, if the value of b is greater than 1, the function will represent growth. However, if the value of b is less than 1 but greater than 0, if it's in between, then the function will represent decay. So now let's go ahead and replace a and b with 1 and 2 respectively, and we can rewrite this function as y equals 2 to the x, just simplified form, and we are going to use this equation to model the growth of our zombie population and see just how long it would take for the entire US population to become infected. So now let's go ahead and graph this exponential function. We are going to label our x-axis as the number of zombie encounters and our y-axis as the zombie population. So now let's go ahead and work on filling out our table. We can start with the value x equals 0, which represents the time before there were any zombie encounters. So in terms of our equation, we have to replace the exponent with 0, and then we can evaluate, and we know that 2 to the 0, or anything raised to the power of 0, just equals 1. So before there are any zombie encounters, we always start with our first infected person, and we should also realize that any exponential equation in this form is going to pass through that point 0, 1, because anything raised to the 0 power is always 1. So these kinds of graphs do not pass through the origin. They always pass through the point 0, 1. And we can reinforce this concept by thinking about that term, patient 0, being assigned to the first person who gets infected. Again, because anything to the 0 power is going to be 1. So once that initial zombie has his first encounter with a human, our population grows to 2. After our second encounter, our population grows to 4. After our third encounter, 2 to the 3 power is 8, so our zombie population is 8. So now we can continue this process of inputting x values to find the corresponding y values so that we can see what other points that our graph is going to pass through. And we can continue this process and complete our graph. So from our graph here, we can see that our initial population growth was slow and steady over the first few encounters, but quickly becomes quite rapid, resembling that hockey stick curve that we spoke about earlier. So now that we have run out of room on our graph, we can go back to the table and look at just how quickly the zombie population is growing as the number of encounters increases.
So in that video, they told us a handful of things. One, we got to see how exponential growth happens when they were looking at the actual population of zombies. And we got to see how exponential decay could happen, which is what happened when they were looking at the population of people, right? Because the amount of people were going down as the population of zombies were going up. We also got to see what the general form of an exponential function is. But right now, what I'd like you to do is I want you to hop back onto Google Classroom and look at the first Khan Academy that's there. It says exponential growth versus decay. And what I want you to do is I want you to give this one a go. So in this task, you're going to be given 4 problems, and they're all going to be equations. So you're going to take a look at each equation and you're going to decide, is it modeling exponential growth? And they might give you a graph, or they'll just say that it's exponential growth. Or is it modeling exponential decay, which means that it looks like it's steep at first and then it's decreasing very, very quickly and then flattening out. Okay, so this would be exponential decay. Now, think back to that video, okay? He told us something about this right here. This base number is what we call our growth factor. And he only mentioned it very, very quickly. But if this number is bigger than 0 but smaller than 1, okay? So if that base number is bigger than 0 but less than 1, it's going to be a decay factor, which means that it's going down because it's a fraction every single time. If that b value is greater than 1, it is going to be a growth factor, okay? Because it is going to be increasing by whatever that is, being raised to a power every single time. So if it was 2, it would be doubling every time. If it was 3, it would be tripling every time. If it was 0.5ing, that means that it is halving every time, okay? So really, it doesn't matter what it's saying here. It doesn't matter if there's anything going on over here or to the exponent. You're going to look at just this base number, and you're going to ask yourself, okay, is that a fraction or a decimal between 0 and 1? If it is, it's a decay. This is 0.5. That's between 0 and 1. I would click decay and check it. Or is that number greater than 1, which means that it has to be growth. You're going to see no negative numbers here because we're not going to see exponential functions that have a b value of a negative. That's just not possible. To get the decay, you end up with a decimal between 0 and 1, and to get the growth, you get a number larger than 1. So you have 2 choices. You can pause the video, work on this right now, and then come back, or we can just continue on with the video, and then you can go to Khan Academy afterwards, okay? This is one of your 2 homework sections. So now that you've looked a little bit about what does growth versus decay look like, both in the graph and seeing it a little bit in the equation, I want to dig in a little deeper for actually like how do we go about graphing exponential functions, okay? So we've done a lot of graphing this year. This will be the last graphs that we're looking at. Is going to be exponential growth function and an exponential decay function. So I want to remind you that an exponential function is generally in the term y equals a b to the x, where a is some number. And if we think back to that video, it's the amount of people you start with that are being infected. If we're thinking of the zombie apocalypse, this also can be what you start out with initially, okay? Initially, there we go, your initial amount. So if we're talking about increasing something and you start out with 5, your A value would be 5. B is always your growth factor. And remember, your growth factor can be a decimal between 0 and 1, meaning that it's a decay, or it could be a number that is greater than 1, which means that it's going to be exponential growth. And then X is always X, so you're always going to have X in your exponent. Again, it's going to be exponential growth if your B is going to be greater than 1. And there's something interesting about exponential functions that we haven't ever seen in a graph yet, and it's an asymptote. And sometimes there's little nerdy memes about asymptotes. I've seen them on math pages on Facebook. If you've ever heard the word asymptote, what it is it's kind of like a dotted line that a graph gets really, 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 really close to, but never actually hits, okay? So an exponential function is going to have an asymptote right here. Okay, this is the parent function, so this is the simplest exponential growth function that exists. And it has an asymptote at the x-axis, which means it's going to get closer and closer and closer to it, but it's actually never, ever going to touch it. And I know that seems really, really weird. Like, if it's getting closer and closer, how's it never going to touch it? Well, think about if you half something, and then you half it again, and then you half it again, and again, and again, and again. At some point, you're going to be at like 0.0000000 some number, right? But you're never actually going to be exactly at 0 because you're never subtracting. You're just dividing by 2, okay? So you're always going to have an amount. It might just be really, really small. So an asymptote, again, is going to be a line that your curve approaches but never hits. Okay, so a line that your curve approach is, but never hits. So this is the general form of an exponential growth function. Okay, usually it's modeled with 3 points. If you think back to our last chapter, right, when we had graphs of square roots, we modeled that with 3 points. When you're doing a curve, folks, it has to be at least 3 points, okay? So it's continuous, which means all of the points in between every dot you would do would be connected, okay? It's 1 to 1, which means for every single one of x's, there's exactly 1 y, and if we read it left to right, it's increasing, okay? Again, this is an exponential growth function, so it's going to be increasing. Generally speaking, the parent function has a range that's all positives and the domain is all reals. Now remember, it's never going to hit this x-axis, so every number that's bigger than 0 would work, okay, but not equal to it. It does have an asymptote, and then its intercept is at 0, 1. Now, these 3 values here, okay, are really important. And these x values right here are also really important. So what we're going to do is we want our x values, or if you look here, right, that's our exponent, to equal -1, 0, and 1 every time to get our 3 main points for this graph, okay? And then there is a pattern that happens with our b occasionally for each of these, but it's influenced a lot by whether there's adding, subtracting, multiplying, or dividing. So let's take a look at how to graph one of these, keeping in mind that -1, 0, and 1 are going to be x values that we're going to kind of shoot for. So we're asked to graph each of these functions and state the domains and ranges for each. Let's take a look at this first one, okay? So our goal when we do this is we're going to create a table again, just like we did for our other graphs, a little XY chart, and it's going to have 3 points in it. Now, to pick our x values, you're going to take your exponent, which in this case is nice and easy, right? This is the easiest exponent, it's just x. But you can see here we have an x minus 2, we have an x plus 3, you could have a 2x, okay? You're going to take whatever your exponent is originally, and you're going to set it equal to -1. You're going to set it equal to 0, and you're going to set it equal to positive 1. Again, these three values are from the three values they gave us in our parent function, -1, 0, and 1. So, because our x's are, or our exponent is literally just x, we just get to use -1, 0, and 1. This one's a little bit more simple. You'll see over here, we're going to have to add 2 to each side to figure out what that number is we're going to put here. So now that we have each of these, we're going to plug it in and solve, okay? So you are going to have to do some PEMDAS work here, just like we did with square roots. You want to make sure you take your time because it's a bummer if you get this part wrong, okay? So I'm going to have 2 to the -1 plus 1. Now you might say, Mrs. White, I don't want a negative exponent, okay, because that makes you feel weird. Totally get you. I understand, okay? But this negative exponent just means change the location. If you think back to chapter 4 when we did polynomials, or if you did it with Mr. Andreessen or Mrs. Boyce, when you had a negative exponent in the numerator, you would move it to the bottom. If you had it in the denominator, you move it to the top. That's all we're going to do here, folks, okay? So don't stress out too much about it. This just says change the location of that 2. So instead of the 2 being in the top of the fraction, it's going to be in the bottom. There's nothing left in the top, so we stick a 1 there, and then we're going to add 1 to it. So 2 to the -1 is the same thing as 1/2. Hopefully that's familiar. And then 1/2 plus 1 is 1.5. So we'll graph that. You know what? Maybe we'll wait to graph all of ours to see what we need to do for a good scale. Let's take a look at our next one. I'm going to plug in 0 for x right here and simplify. So I'm going to have 2 to the 0 plus 1. Well, just like he reminded us in our video, and again, this overlaps a lot with Chapter 4's exponent properties, anything to the 0 power is just 1. Always, every time. And then I'm just going to add this one after it. That's going to give me 2. Now I'm ready for my third point. I'm going to put my 2. Oops, this should be positive 1. Sorry. -1, 0, and positive 1. 2 to the first power plus 1. Well, 2 to the first power is just 2, and 2 plus 1 is 3. So it looks like I don't have to go very far on my x-axis. I'm just going to go -1, 0, positive 1. For my y-axis, it's all going to be positives, and I need to go up to at least 3. So 1, 2, and 3. And I'm ready to plot my points. So I'm going to go over to -1 and up 1.5 boxes, approximately there. Then I'm going to go over to 0 and up 2 boxes. So over 0, up 2 boxes. And then for my third point, I'm going to go over 1, up 3 boxes. So over 1, up 1, 2, 3 boxes. So here's the general shape of our curve. It's going to be going whoop up like this. And if you think about it, that makes sense, right? If this is our b value, it's bigger than 1, so it should be exponential growth. So it's going to be getting steeper to this side, and this side should be flattening out. Now I want to take a second and go back and look at our parent function. I told you there was something really different about it with this asymptote right here. Okay, now this is one piece aside from making the table that you're just going to have to memorize. Okay, whenever you have an equation and you add or subtract on the outside, that is going to move your asymptote. So this +1 shifts our asymptote up 1. If we had a -5, it would shift our asymptote down 5. If you have nothing being added or subtracted, okay, remember, not to the exponent, but just added or subtracted at the end, then it's going to stay right on the x-axis. So here, our asymptote was shifted up 1. So I actually have to draw that. It's normally here, so it's going to be shifted up 1. That means it's going to be a horizontal line right there. And because it's a horizontal line, okay, I model it with a y equaling and then just a constant. So y is going to equal 1 here. Okay, that's the equation for our asymptote. So it's going to get really close to that one, but never hit it. It's really important that you draw the asymptote in as a dotted line, because otherwise you could accidentally sketch your graph going below it, and that's impossible in an exponential function. Okay, so here's 3 big ideas. Let's just summarize this really quick. You can put it as bullet points in your notes if you'd like to. The first thing you're going to do is you're going to set your exponent equal to -1, equal to 0, and equal to 1. That's going to give you your 3 x values. Then you're going to plug those in and get out your y's, 3 coordinate pairs. You can graph those 3 points if you want to, but I'd stop at that point and look, are you adding or subtracting to the very end of your equation? If the answer is yes, then you're going to shift your asymptote either up or down based on if it's plus or minus, and it's going to be up if it's plus and down if it's minus. Okay? And then graph your asymptote as a dotted line, and your 3 points, making sure to sketch in the rest of the shape. Okay? So let's take a look at one that's a little bit different. Over here, my first step we just talked about is we're going to make a XY table. We have to find 3 x values that are going to make sense here to give us the -1, the 0, and the +1. So I take my entire exponent, x minus 2, and I'm going to set it equal to 0. I'm going to take that same exponent, I'm going to set it equal, I should have done this first up top. We'll make this one -1, then 0, and then +1. So to figure out what x value is going to work to give me the -1, I'm going to add 2, -1 plus 2 is 1. Here I'm going to add 2, 0 plus 2 is 2. And then here I'm going to add 2, and I get 3. So these are the exponents I'm going to use to plug in here. So now I'm just going to plug those in and get my actual points. So I have -1/2 times 5 to the 1 minus 2. And remember, 1 minus 2 gives me a -1. I know that, right? I made it that way. So I'm going to have 5 to the -1. Well, anything to the negative power means kind of take the reciprocal, right? Stick that 5 in the bottom and put a 1 up top. So I technically have -1/2 times, instead of 5, it's going to be 5 to the -1, which is the same thing as 1/5. Now I go across the top and across the bottom. A negative times a positive is a negative, 1/10. That's a very small point, 0.1, okay? So I'm going to go over 1, up 1, down 1/10. Now I'll do my next point. I'm going to plug a 2 in here. So 2 minus 2 is 0. So I have -1/2 times 5 to the 0. Anything to the 0 power, right, is 1. So I technically have -1/2 times 1. And anything times 1 is just itself, so -1/2. Now I'm ready to do my third point, and then I'm going to look for my asymptote. So I'm going to stick a 3 right up here. 3 minus 2 is 1. So I have -1/2 times 5 to the first power. Anything to the first power is just itself, so I technically have -1/2 times 5, but I'm going to put my 5 over 1 because when I multiply by a fraction, I go across the top and across the bottom. So negative times a positive is a negative, 5 halves. And hopefully you folks know that 5 halves, or 5 divided by 2, is just -2.5. So now I'm ready to start graphing these. JK, I got to do my asymptote. I should probably do that first. Let's set up my graph. So my x's are all positive, so that's why I made such a positive quadrant here. I got to go up to 3, so 1, 2, 3 on my x's. Then my y's are all negative, which is why I didn't include it going up here. And it goes from -1/10 to -0.5 or 1/2 to -2.5. So I'm going to go down -3. 1, 2, 3. And that should be enough to plot all my points. Now my question to you is there anything being added or subtracted at the end here? Not to the exponent, but outside of the exponent, right? Is there a -3 or a +1? Well, clearly there's not, which means that our asymptote is going to stay right on the x-axis, okay, at y equals 0. You always have to have that line in there as a dotted line to model your situation. So now I'm ready to plot my 3 points. I'm going to go over 1 on the x, and I'm going to go down 1/10, which, I mean, 1/10 is like really close. It's 0.1, right? 1 divided by 10 is 0.1. Next, I'm going to go over to 2 and down half a box. So over to 2, down to half. Then I'm going to go over to 3 and then down 2.5 boxes. So over to 3, down 1, 2 and a half. That changed very quickly. And there we go. So let's take a look at this equation. You might be like, this does not look like either of my functions, Mrs. White. Well, I want to let you know something. When we subtract or add up here, that's a shift left or right. So this actually moved to the right too. And then when we multiply by a negative, it's always a reflection, okay? So it could be either reflected upside down, which is what happened here. It's upside down. Or it could be a reflection over the y, which would kind of make it look like a exponential decay function, okay? And then when we times it by 1/2 right here, that changed the steepness a little bit. But remember, our growth factor here was still 5. So this is still technically technically, this is still an exponential growth function because this number is greater than 5. It's just reflected because of the negative over the x-axis. Okay? And that's perfect. Good to go. What I'd like you to do, folks, is I would love for you to pause the video and try each of these. I'm going to go through and put my work down for each of them, and then I'll talk you through how I did the work. But I'm going to speed it up a little bit, and I'd love, again, for you to try it on your own. All right, folks, let's come together, okay? So, first things first, we could take a look at our b value, right? It's greater than 1, so again, it's going to be exponential growth. All of these are exponential growth because that's what we're looking at right now. I took my exponent, and I said it's got to be equal to 1/2. My exponent's got to be equal to 0, and my exponent's got to be equal to 1. And I just minus 3 from each side to get these 3 values. Boom. Then I plugged each of them in PEMDAS, so -4 plus 3 is -1. 2 to the -1 is 1/2 minus 5. If I'm at a positive half and I go backwards 5, I'm at -4.5. Then I plugged in -3. -3 plus 3 is 0. So 2 to the 0 minus 5. 2 to the 0, anything to the 0 is 1. 1 minus 5 is -4. And then lastly, I plugged in -2 here, which gave me a positive 1. So 2 to the first minus 5 is the same thing as just 2 minus 5, or -3. So here you can see my function. I also kind of did it early. I said, oh, look, there's subtracting on the outside. That means I'm going to move my asymptote down 5. It's going to be at the line y equals -5. And that actually was the first thing that I plotted. Okay? Give a go to this last one right here, and we'll come back together in just a minute. All right, folks, let's come together for this one. I didn't quite finish graphing it because I wanted to make sure to touch base with you around that first point, because I'm sure making this XY chart for you was not your fave, and I could do most of it with mental math, but not necessarily this first one. So right here, I took my -1 and I plugged it in. And when I plug in a negative, it means kind of take the reciprocal of this, right? I'm going to move my 6 below. So it's going to become 1/6. To do 1/6 times 0.1, I need to either have both things be a fraction, or I need both things to be a decimal. Okay, I can't have one of one and one of the other. So I personally would probably do make this 1/10, because I know 0.1 is 1/10, and then I'd go across the top and across the bottom, and I would get 1/60 minus 3, and then I would get 2 and 59/60. Okay, so I know that's going to be really close to, or -2 and 59/60. But that's probably not what you would do. Okay, you wouldn't say, oh, I'm going to make it into a fraction. I love fractions so much. You probably would say, all right, I got to make this fraction right here an actual decimal. So I'm going to go through and do that with you because I assume that's what you did. So we're going to do 1 divided by 6 is 1.6 repeating. So 1.66666, okay? So I'm going to take that 1.6 repeating right now, and I'm going to times it by 0.1. And I got 0.01 with this 6 repeating on forever, okay, minus 3. So I still have this in here. I'll just minus the 3 right from it, and I get -2.98 and a 3 repeating. So we're just going to keep it as -2.98. So now I'm ready to graph these. I'm going to go over to -1. I'm going to go down 1, 2, pretty much 3. It's really close to this line, but remember, it's never going to hit the asymptote, which I had to move down 3 because I subtracted 3 on the outside. The next point I'm going to do, I'm going to go over to 0, and I'm going to go down 2.9. So over to 0, down 2.9. That's just like the tiniest hair above this one, right? This is our very flat section. Then I'm going to go over to +1 and down to 2.4, which is like, this is even not even close to 2.9. It should be even lower than that. 2.4 should be a little bit less than half. So you can see that this is going to be that flat part that just hugs that line, and then it's going to slowly decrease, and then it quickly increase, excuse me. It'll start out slow, and then it's going to speed up. That's the idea of exponential, right? It's going to increase drastically as it continues on that way. And that's how we go about doing this. So even if you're going to be dealing with a fraction and decimals, folks, it's totally capable. You're totally capable of doing that, okay? So don't be too intimidated. So this has been an entire section on exponential growth, okay? And there is a parent function for exponential decay. So if you look at it, right, exponential growth started out slow, whoosh, and went really steep. Well, exponential decay starts out very steep, and then it slows way, 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 way down. Okay, and if you read it left to right, it has a general decreasing or a negative correlation to it, right? It's going down. It's still continuous. It's still one-to-one. The domain is all reals and the range is still positives, and the asymptote is in the same location, okay? In fact, everything is pretty much the same, except your b value is going to end up being a decimal or fraction between 0 and 1. We're still going to do our same three x values, 0, -1, and 1, okay? With our exponent, we actually graph these the exact same way as we do exponential growth, okay? It's just going to give us a little bit different shape, and that's like that reflection over the y-axis, right? So we're going to do just 2 of these, and then I'm going to have you hop on Khan Academy and start your last skill. Khan Academy has you doing these a little different than I am, or it gives you a little bit more freedom. So what I want to do is do these 2, and then we'll do one Khan Academy one together. So first things first, I'm going to notice, okay, here's my b value, right? My x is in the exponent. It's exponential. This b value is between 0 and 1. It's a fraction or a decimal between 0 and 1, so that means it's going to be decay. So in my head, I'm thinking, all right, it's going to be like this shape, right? So I'm going to take my exponent in its entirety, and I'm going to set it equal to -1, 0, and 1 so that I can make my table. Well, luckily, this exponent is just x, right? So I'd have x equals -1, x equals 0, x equals +1. I don't need to move anything over. They're already moved over, right? My x is already alone and positive. So I'm going to use -1, 0, and +1 as my x values here. Then I just plug them in. It literally is the exact same stuff as before. Now, I know you're like, Mrs. White, it's not the same. We're dealing with fractions, okay? And I feel ya, but we were dealing with fractions, okay, at least once on each of these. See, we had this 2 that became a 1/2, right? We had this 2 that became a 1/2. We had this 5, which became a 1/5, right? Right here. And then we had this 6 that became a 1/6. So we can handle fractions. You can handle fractions. You're capable, okay? So we're going to start by plugging our -1 here. So I have 1/3 to the -1. Negative power would go here and here. So the -1 on this one would mean move it below. The -1 exponent here would mean move that up. So this just literally becomes 3, right? I take the reciprocal. I'm going to take that 3, move it to the top, take that 1, move it to the bottom, change the locations with that negative exponent. So I'm done. That's it. My coordinate pair is going to be -1, 3. Let's look at our next value, 0. So 1/3 to the 0 power. Well, what's anything to the 0 power? It's 1. That was nice, okay? Now we're going to plug in 1 here, okay? So we're going to have 1/3 to the first power. Anything to the first power is just itself. So we end up with a fraction there, okay? You're going to end up with a fraction either way on each of these problems, right? Whether it's growth or decay. In growth, the fraction happens here. In decay, it happens when you get to your +1 power. So my question to you is, now we have to figure out our asymptote, right? Is there anything being added or subtracted here? No. So that means our asymptote is going to be on our x-axis. My x's go -1 to +1, and my y's are all positive up to 3. So I don't have to include any negative y's. 1, 2, 3. -1, +1. And I'm ready to graph. So I am going to start off by graphing my asymptote. Remember, there's no plus or minus here, so I got to do a dotted line right on the x. And I would put y equals, and that y value there is 0. Okay, now I'm ready to plot a point. I'm going to go over to -1, and I'm going to go up 1, 2, 3 right there. I'll plot my next one. I'm going to go over 0, up 1. And then I'm going to do my third one, which is over to 1, up 1/3 of a box. And you can see, oh yeah, there's that steep going down, and then it's going to start evening out. Remember, it gets closer and closer to that asymptote, but never actually hits it, okay? And this is going to be increasing really, really steeply to the left here, okay? Same exact idea, right? Except instead of starting little and going up, it starts by, very steep, and then evens right out at the bottom, okay? If you want to, feel free to pause this one, but I am going to go through this one in its entirety right now. So I'm going to look at the exponent. I notice this b value right here is less than 1 but greater than 0. So it's going to be exponential decay. I'm thinking of this shape again. I'm going to take my x plus 2 and I want it to equal negative 1. I'm going to take my x plus 2 and I want it to equal 0. And I'm going to take my x plus 2 and I want it to equal positive 1. So to get my x values for my table, I'm going to subtract 2 from each side. And that's going to give me negative 3. If I minus 2 minus 2, I'm going to get a negative 2. And if I minus 2 minus 2, I'm going to get a negative 1. Okay, so negative 3, negative 2, and negative 1 are going to be my exponents that I plug in to get what I need. So let's plug them on in. This is going to be longer. You can see that I'm multiplying. There's a fraction. I'm subtracting. Ooh, I'm subtracting. That means my asymptote is going to be shifted down 3. It's going to be at y equals, and then this exact value, negative 3. So keep that on the back burner. All right, now I'm going to plug them in. Negative 3 here. So negative 3 plus 2 is negative 1. So I have 2 times 1/4 to the negative 1. And then I have a minus 3. So PEMDAS says exponents. So anything to the negative power, I'm going to change the location. It becomes 2 times 4 minus 3. PEMDAS also says multiply before subtract. So I have 8 minus 3. And 8 minus 3 is 5. So this coordinate pair is negative 3, 5. Let's take a look at our next one, negative 2. So if I plug negative 2 here, negative 2 plus 2 is 0. So I have 2 times 1/4 to the 0 minus 3. PEMDAS says exponents first. Anything to the 0 power is just 1. Then multiply before subtract. So 2 times 1 is 2, and 2 minus 3 is going to be negative 1. Let's take a look at our last one now for this section. Okay, I'm going to plug a negative 1 here. Negative 1 plus 2 is positive 1. So I have 2 times positive 1/4 to the positive 1 power. Now, anything to the first power is just itself. And so I really just have 2 times 1/4 minus 3. And then to do 2 times 1/4, I'm going to put that over 1. I get 2 over 4. And 2 over 4 is the same thing as 1/2. Minus 3. If I'm at positive 1/2 and I go backwards 3, I'm at negative 2.5. And now I'm ready to graph it up. Okay. My x's are all negative, so I'm really going to focus over here. I have to go all the way from positive 5 to negative 2.5. So 1, 2, 3, 4, 5. And then negative 2.5. 1, 2, 3. And I go to 3 because I also know my asymptote's going to be down there at negative 3. So I'm going to put that right on in right now. Ooh, that's not where it should be. It should be at 3. Just imagine that I drew that line much better than I did. Okay. And then I got to go negative 3 here. So 1, 2, and 3. All right, now I'm ready to graph. I have my asymptote at negative 3, and I'm going to go over to negative 3 on my x and up to 5. So negative 3, 5 is here. I'm going to go to negative 2 on my x right here, and I'm going to go down 1. And then I'm going to go over to negative 1 and down 1, 2.5 boxes. So you can see, wow, starts out super duper 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 steep. And then, ooh, it's evening out right here, and it's going to just hug that line but never actually cross it. Okay? And that, again, is our exponential decay. It starts out very steep, and then it, flattens right off. So your homework tonight is to have identified your growth and decay, that Khan Academy piece we just talked about, okay? And then I want you to do this one, graphing exponential growth and decay. Now you can see here, they're going to be giving you a bunch of functions, and you're going to be asked to graph it. So you're going to drag these 2 dots to just 2 points. So if you want to do, the exponent equals 0 and the exponent equals 1, that'd be fine with me, okay? But either way, you only need to do 2 points and you'll drag it. So let's do one of those together really quick. and make sure you're feeling good about how to interact with the site. I want you to slow down, right? Because you need to get a 75 or better on this. And so if you can just get, 3 of the 4 right the first time, you only end up having to do 4 problems for homework. If you end up getting it wrong, then you end up having to do more, okay? And the goal is that you're being really thoughtful and very methodical, which means you're following the correct method, okay, to get to that answer. So you have to do less problems and you're practicing it really, really correctly. So we're going to treat this just like we normally would. You're going to ignore this graph for now. So I'm going to look right here at this fraction, and I'm going to say, oh, it's a fraction. Now, that doesn't mean anything necessarily in Khan Academy. You want to ask yourself, is it bigger than 1 or is it less than 1? So 4/5 it's not improper, right? It's not top heavy, so it's less than 1. So this is going to be exponential decay. So it should look steep to flat, okay? Next thing I would encourage you to do is look, is there any plus or minus here? If there's a plus or minus, say it's +2, you would move your, or maybe it's a +1, you would move this, and I'm just clicking on it and dragging it, not that. You're going to grab your asymptote, right? And you're going to drag it wherever it goes. So if there was a +2 here, I would drag it +2. If there was a -3 here, I would drag it down to -3. And it's not letting me do it until I move that dot up there. There we go. -3. Okay? There's nothing, so my asymptote's going to stay right on the x-axis at y = 0. So I know where my asymptote is. I know that eventually it should look like this, right? Somewhat like that. Now I'm ready to figure out my 2 exact points. So I just turned on the sketch thing since I have this tablet I'm using. And my x is just x. So to create my table, it's going to be pretty quick and easy. I'm only going to do 2 points. Let's do 0 and 1. Okay, now remember, if there's a +2 here, I'd have to do x + 2 = 0, x + 2 = 1. All right? Ooh, that's not good. We're almost done. So I'm going to put a 0 in here. Anything to the 0 power is 1. So I technically have 5 times 1, which is 5. So I'm going to go over 0, up 5. My next point, I'm going to plug in a 1 here. So I'm going to have 4/5 to the first power. So I'm going to have 5 times 4/5, because anything to the first power is just itself. I got to put this over 1. I'm going to go across the top, across the bottom. So I get 20 over 5. And 20 over 5 is just 4. So I'm going to go over 1, up 4. So if I look, does it look like it's going up steeply to the left? Yes. And it's going flatter to the right? Yes. My asymptote is not shifted up or down because there's no plus or minus here. And this is a decay. And in my head, I know it should be a decay. All right. So I'm ready to check it and give it a go. Yay. Okay. Now I'm ready to do the next one. And you're going to follow the same suit, right? Okay, is there any plus or minuses here? Do I move my asymptote up or down? Create your little table with just 2 points and slide those around. If you have any questions, folks, please feel free to stop by at office hours. You can even do your Khan Academy and share your screen with me, and I can check it before you press send. I'm perfectly fine with that. If you're not taking advantage of those office hours, though, folks, and you're struggling, I would really encourage you to hit me up, okay? That time is set out for you folks, for Algebra 2 College Prep, so please take advantage if you need it, okay? Otherwise, make sure you take a screenshot when you're done and attach it to me on the Google Classroom. Thank you, folks. Have a great day, and I will see you, talk to you, whatever, either during office hours tomorrow or on Monday when we do our last new learning for the year. See you then. Bye.